Welcome to this new reality TV show called Redox Rescue. Studies have shown that this reality TV show is more popular than Big Brother, Survivor, or even Party Down South. So let's get to the point at hand here, which is really to have a better understanding of oxidation reduction reactions. Let's consider this one first. Let's say we have calcium plus something else, and to be honest with you right now, I don't care what that something else is, okay? Because I want us to consider a simplified general example. Let's say that yields as one of the products calcium sulfate. So the question at hand is calcium in this reaction over here, this calcium as a reactant, is it oxidized, which would mean losing electrons, or is it reduced, which means gaining electrons in this particular example? Now normally we would balance the reaction, but this is a generalized example, so we don't really know what's reacting. I just want us to focus with laser-like focus here on the calcium situation, okay? So let's look at this though, okay? We know that when we see calcium sulfate, you have to know, I hope you know, that this is calcium 2 plus SO4 2 minus, okay? And so with calcium sulfate, calcium is an ion. But over here in the reactant, this is just elemental calcium metal. It's an atom. It has no charge, so it's 0. Okay, so every time we do one of these analysis of these types of reactions, we do a half reaction. Let's just consider calcium in our simplified example here. Okay, so it looks like we have calcium 0 going to calcium 2 plus. I don't care about anything else right now but calcium, okay? Because that's the question at hand. Is it oxidized or is it reduced in this particular reaction? Well, I've got the charges shown, the atoms are balanced. Of course, we didn't balance this reaction, so that doesn't matter here. But what you will notice is that we have an imbalance of charge, because on the left we have 0 and on the right we have 2 plus. So this is an imbalance, okay? So does not equal. Let's do that. Boom, right there. Does not equal. So in these types of reactions, we have to add electrons on either side such that we get a charge balance, okay? So I'll tell you what, let's just freestyle here. Let's just say you decide to add the electrons on the left, okay? And I think you see where the only thing that, well, let me back up. The only thing we can do at this point is add electrons to one side or the other. Our currency is electrons. That's the only thing we have to trade. That's the only thing we've got to use. And we have to add electrons to one side or the other. And I think you see, hopefully, that we're off by 2 charges here. So I want to add 2 electrons somewhere to get everything all balanced out. So I'm just going to start on the left. And let's see what happens. If we start here, what it looks like to me is by adding the 2 electrons on the left, we're going to have a 2 minus on the left, and we're going to have a 2 plus on the right. Well, ladies and gentlemen, that does not equal each other. 2 minus does not equal 2 plus. So you cannot put the 2 electrons on the left. That is not going to get the job done. So I'm just going to erase it because that's bad chemistry. Okay? So let's try this. Let's add those 2 electrons on the right, and let's consider the charges. Well, it looks like we've got 0 on the left equals 2 plus a 2 minus. Well, guess what? We got it. That's it. 0 equals 0. So the charges are balanced. So the 2 electrons had to go on the right. And so what this is telling you and it's telling me is that calcium 0 here had to lose 2 electrons to become calcium 2 plus. And again, this should make sense because if something that has an equal number of electrons and protons gives up 2 electrons, then it is left with 2 extra protons. So it should be 2 plus. Therefore, we know calcium has lost 2 electrons here. And so what we would say is that calcium, on the left, the reactant, calcium is oxidized because it has lost 2 electrons. And we know oxidized is the same thing as saying the reducing agent. Now this, again, this was just kind of a general, somewhat simplified example just to get us thinking about what do we need to do in these half reactions. We have to add electrons to make the charges balance. Okay? Well, let's go to a more complicated problem. So let's just gently go down here. How about this reaction? What if we had iron plus nitrogen? And I know this has been throwing some of you off. In class we talked about Br2. Today we talked about O2. Well, it turns out that the elemental state of some nonmetals like oxygen, nitrogen, and hydrogen, and the halogens is what we call a diatomic molecule. So we know that the charge here is going to be 0 because this is elemental iron, metallic iron. It's an atom of iron. Okay? It's just iron, Fe. So it's 0. N2 is also has a charge of 0. It is the elemental state of nitrogen is N2. This is not an ion. It's just N2, 2 nitrogens bonded together. Okay? Now, in this reaction, this is going to yield Fe3N2. Now, I hope you pick up on something here. It's like, okay, warning, we now have an ionic compound. So now we have an ion of iron and an ion of nitrogen. Okay? Now, before we break this apart, let's do our job of balancing. We need to add a 3 right here, and now we have atom balance. 3 irons on the left, 3 irons on the right, 2 nitrogens on the left, 2 nitrogens on the right. But this is where I think there's some confusion. Again, this is Fe3N2. You should see a metal and a nonmetal and say, okay, that's an ionic compound. I've got to deal with ions. And he's given me the formula. He's been very nice to me. Look at this. I need to break this apart into the ions. So this is going to be 3Fe2 plus. How did I know it was 2 plus? Because it's Fe3N2. I know I have iron 2. Okay, because it's Fe3N2. Because Fe3N2 had to have a charge balance to write the ionic compound. Okay? And what we're doing is going to demonstrate that. So we got 3 Fe2 plus and 2. Now here's one we've went over, the nitride ion. Everybody get your green sheet out. Okay? That's a nitride ion. That's not a nitrogen atom, it's the nitride ion. We are dealing with ions on the right. I feel like I'm beating a dead horse on this, but I want to make this clear. Okay? So here we go. In this reaction is iron, the reactant iron on the left, is it oxidized or reduced? N2 on the left, a reactant, is it oxidized or reduced? We're going to have to write half reactions. That's the only way you're going to get this right. So you're going to have to do it this way, I think. So we got 3Fe0 going to 3Fe2 plus. Now you notice that we have we have balance of irons. 3 irons on the left, 3 irons on the right, and we did that because we did a good job of balancing the reaction to begin with. Okay, you notice there's no nitrogen here. I don't care about nitrogen here. This is a half reaction with iron. Okay, now I also hope you notice that we have a charge imbalance because the charge on the left is 0. 3 times 0 is 0, and the charge on the right is 6 plus. That's an imbalance. That also is my clue that, okay, I'm going to add 6 electrons somewhere. I know that now because we have too many positive charges on one side. We have an imbalance of 6. I'm going to add 6 electrons somewhere. And if you look at this reaction, adding it on the right is really the only way this can work. If we add 6 electrons on the right, that's the only way to get charge balance. Try to do it on the left and see what you get. That's not going to, we're not going to balance the charges, okay? But adding the 6 electrons on the right will balance those charges because we would have now 0 equals 6 plus, 3 times 2 plus is 6 plus 6 minus. Hey, that's 0. 0 equals 0. We got it. Okay, now, well, what had happened to the iron? The iron lost electrons. So the iron is oxidized, which means it is the reducing agent. Also notice, 6 electrons are involved. That's a good question that I could ask you. How many electrons are involved in this oxidation reduction reaction or redox reaction? Well, I now know there's 6 electrons involved. Because iron lost 6 electrons, guess what's going to accept 6 electrons? The N2. Because the extent of oxidation always equals the extent of reduction. Well, let's go over that. So, what do we got here? We've got N2. We're still doing the same one here. I'm just doing the other half reaction. N2 yields 2 N3 minus. This is 0 because that's the elemental state of nitrogen. N2, it's elemental. It yields 2 nitride ions. We got all this from the original reaction. Okay. Well, we've got nitrogen balance. Feeling good about that. I'm not feeling too good about the charge balance because 0 does not equal 6 minus. So we've got to add 6 electrons somewhere. And I hope you see that adding them on the right is going to be very, very, very problematic. We can't add them on the right because that would not give us a charge balance. But if we did add 6 electrons here on the left, then things are looking pretty good because now 6 negative equals 6 negative. We're just looking for charge balance. We're not looking for getting 0. We're looking for charge balance. So now the 6 electrons lost by the iron is picked up by the N2 to make 2 nitride ions. So what we would say is that N2 is reduced. It gained 6 electrons to produce 2 nitride ions, 2 N3 minus. And reduced is the same thing as oxidizing agent. Again, there is there are 6 electrons involved in this oxidation reduction reaction, or redox reaction. I hope you notice something. Every time I ask you if something is oxidized or reduced, it all boils down to you having to look at the reactants. The question every time is about the reactants of a reaction. Is this reactant oxidized or reduced? Is this reactant oxidized or reduced? If one is oxidized, the other has to be reduced. So I would not ask you at any time, at any place, anywhere, is the nitride ion oxidized or reduced? That's not going to happen, because the question about oxidation and reduction always has to deal with the reactants of the redox reaction. I hope this episode of Redox Rescue has been helpful for you in tackling oxidation reduction reactions.